The first talk is titled Federated Learning for Skin Cancer Detection with the HAM10000 Dataset. That's a cool name. And it's going to be given by Priyanka Das from the University of Texas at Dallas. So Priyanka, the floor is yours. I'm going to stop sharing my screen and you can share yours.
Okay, so hi everyone. This is Priyanka Das, and I recently completed my master's in business analytics and artificial intelligence from the University of Texas at Dallas. Today, I'll present my project titled Federated Learning for Skin Cancer Detection using CNNs. This work explores how we can train deep learning models across multiple simulated hospitals without sharing patient data using a privacy preserving approach called federated learning. So let's dive into why is this used in healthcare. So as we all know that healthcare data is highly sensitive. Centralized training methods often require aggregating data in one location, which raises serious privacy, legal, and ethical concerns, especially under regulations like HIPAA and the GDPR. So this is where federated learning or FL comes in. Instead of moving data, FL brings the model to the data. It enables collaborative learning across hospitals or institutions where sharing raw patient data without sharing raw patient data. Another key reason FL is well suited for healthcare is that the data is inherently non-IID. So, what is non-IID? So, non-IID data stands for non-independent and identically distributed data, a situation where the data varies significantly across different sources of or clients, both in distribution and characteristics. So, non IID means that the data is not randomly or evenly distributed. Each client or hospital may have different classes, different frequencies, or biases in the data. So, different hospitals serve different demographics and use different equipment and protocols, making centralized training model prone to bias and poor generalization. Um, let's move to the next slide. So, let me give you a quick overview of the project setup. So my main objective was to train a CNN-based classifier to detect different types of skin lesions, particularly distinguishing benign from a malignant without ever sharing the patient data. So I used the HAM10000 dataset, which contains over 10,000 dermatoscopic images across 7 diagnostic categories. So as you can see on the right-hand side chart, there's a heavy class imbalance with the majority labeled as NV and much fewer samples for rare conditions like VASC or DF. So, to simulate the real world condition, I created a federated environment with 5 virtual hospitals using the flower framework, where each hospital was treated as a separate client. I introduced realistic non-IID partitioning, meaning each hospital had its own class imbalance. This simulates the real-world scenario where different regions or hospitals see different types of patients. The model was lightweight CNN with 3 convolutional layers and ReLU activations. I applied standard pre-processing steps like resizing, normalization, and tensor conversion. For training, I started with the FedAVG as the aggregation strategy, but later moved to FedOPT to better handle the challenges posed by the non-IID nature of the data. So I had created actually two programs, one for the FedAVG, and then I saw that there was heavy overfitting and class imbalance. So that is why I opted for FedOPT, and I also implemented oversampling there. Um, so this is the architecture of the federated learning. So you must be already aware of the architecture. Now moving to the next slide. This is, let's talk about the data set. So for this project, I used HAM10000 dataset, which stands for Human Against Machine, with 10,000 dermatology images. It contains 10,015 dermatoscopic images across 7 classes of skin lesions, both benign and malignant. These images were collected from Austrian and Australian dermatology centers, making it a strong benchmark for automated skin cancer classification. The seven classes include melanocytic nevi, melanoma, benign keratosis, basal cell carcinoma, actinic keratosis, vascular lesions, and dermatofibroma. One major challenge is class imbalance. The NV class dominates with nearly 67% of all images, while some rare classes have fewer than 150 samples. To simulate a real world federated setup, I divided the dataset into five clients. On the right side, you can see some sample images from the dataset. This gives a visual sense of the diversity in skin lesion appearance and across dataset. So here I'm again showing you, like I already discussed, that NV class has almost 65% of the data. So this non-IIT distribution led to two major issues during training. One is overfitting to the majority class, and the second is like poor generalization on minority classes. To mitigate this, I applied random sampling at the client level. This involved duplicating samples from underrepresented classes within each client's training data to balance class distributions. Importantly, I left the validation and test sets untouched to preserve a realistic evaluation scenario. Upsampling had a significant impact. It improved the model's ability to learn features for all classes, especially the rare ones. It also boosted the performance like accuracy and helped reduce bias towards the dominant classes. Now let's look at the CNN architecture I designed for this project. The table on the left outlines the layers and their roles. The input is 224 into 224 RGB image. I use three convolutional layers, each followed by a ReLU activation to introduce non-linearity. After each convolution, I apply max pooling to progressively reduce spatial dimensions and extract the most significant features. After the convolutional layers, the output is flattened into a 1D vector and passed through a fully connected layer with 128 units. And finally, to the output layer with 7 nodes, one for each skin lesion class. I didn't add a softmax here because cross entropy loss in PyTorch expects raw logits and handles that internally. The visual on the right side show two perspectives. The top diagram simplifies the flow, that is convolution to pooling and then flattening and then finally classification. The bottom diagram gives a more technical view, showing how the image shrinks in size while the feature depth grows, similar to how my model extracts hierarchical patterns from lesion images. Uh, Once the data was distributed to clients, each hospital's dataset was split into training, validation, and test sets, with 80% for training and 10% each for validation and test. Um, these splits were stratified to maintain the original class distribution, and importantly, upsampling was applied only to the training set to balance the class representation. The validation test sets remained untouched to ensure fair evaluation. In terms of evaluation metrics, I tracked accuracy and loss per round per client to observe learning progression and detect any overfitting or divergence. And also macro averaged accuracy, which is especially important due to the heavy class imbalance. This ensured performance was strong not only on the majority class but also on the rare skin lesion types. So this is for the first experiment where I used the strategy of FedAVG. So I trained the model across 5 simulated hospital clients for 5 communication rounds. The entire training took around 19.7 minutes. If we look at the global loss history, we see a steady decline from 0.0304 in round 1 to 0.0143 by round 5, indicating consistent learning. Similarly, global accuracy improved from 66.86% in the first round to 83.47% by the final round. This shows that even with non-IIT data, the client level variation Fed AVG achieved stable and effective convergence. On the right side, I have summarized the per client surface plot results. The accuracy surface plot showed an upward trend across all clients, with final accuracies between 83 to 84%. The loss surface plot showed a smooth decline starting from around 0.85 to 0.033, indicating a convergent stability. So I want to show you the plot. So this was the plot, and as you can see, it started from as low as 0.66 and it went as high as 0.83. So this was the highest. Um, so this is for each round for each of the client. This was the accuracy. Now coming to the second experiment, which I was using the FedOPT strategy. And here also the training ran for 5 communication rounds and it took about 21.4 minutes. Starting with the global loss, we observed a faster and smoother convergence, dropping from 0.0543 in round 1 to just 0.0101 by round 5. This is notably more efficient than what we saw with FedAVG. For global accuracy, FedOPT showed a steep rise from 37.24% in round 1. It climbed to 89.68% by the final round, outperforming FedAVG throughout. On the client level, the 3D surface plot gives us a visual confirmation. Accuracy curves are smoother and more stable across clients. All clients consistently improved with accuracies ranging from 37% to 89%. The learning paths show less fluctuation, meaning FedOPT handled non IID variations better. The loss surface plot also shows a clear drop from around 0.83 to 0.29, and importantly, it was more stable across rounds. Uh, these trends suggest that FedOPT not only accelerated convergence but also maintains synchrony among clients, which is crucial when data is heterogeneous. So for FedOPT, uh, this was the validation accuracy. So it started with 0.36 and it went to as high as 0.90 and 0.93. So for in case of Fed AVG, it never passed like above 0.90. This is one, and this is the training and validation loss plot. So I did this to check if it is like overfitting. So this is for the training loss and this is the validation loss. So as you can see that it is almost similar. So we can say that there is no overfitting here. Okay. So here I present side-by-side comparison to the two federated strategies, FedAVG and FedOPT, to summarize their performance. Starting with training duration, FedAVG completed in around 19.7 minutes, while FedOPT took about 21.4 minutes, just 1.7 minutes more. But this small increase in time gave noticeable gains. Final global accuracy improved from 83.47% with FedAVG to 89.68% with FedOPT. And the global loss dropped further from 0.143 to 0.0101. In terms of stability, FedAVG showed moderate variance in accuracy across clients, whereas FedOPT achieved more consistent learning across all clients. For loss convergence, FedAVG had a gradual and stable decline, while FedOPT offered a faster and smoother drop, especially in early rounds. So when it comes to client synchrony, FedOPT again performed better, showing tighter alignment between clients even in the presence of non-IID data. Overall, FedOPT outperformed FedAVG across all major metrics: accuracy, loss, and learning consistency. It also handled data heterogeneity more robustly, making it more suitable for real world federated setups. That said, FedAVG remains a strong baseline. It's simpler and more computationally efficient, which can be helpful in constrained environments. So, the choice between the two depends on the application, whether you prioritize efficiency or robustness. And I think I have a slide for that as well. So, this one is for FedOPT. As you can see, it started quite low with 0.41, but it went higher till as high as 0.94. And this one was for Fed AVG. So it started at 0.66, but it ended at 0.83, which is lower than Fed OPT. So moving on to the next one. To wrap up, let's go over some of the key lessons learned and limitations of the study. So these were the lessons learned. First, I found that handling non IID client data is absolutely critical. Hospitals had different data distributions, which greatly affected model performance. Upsampling did help, but it required careful tuning. It is not a one size fits all solution. Secondly, client level upsampling before training improved generalization. By locally balancing the distribution, I was able to boost fairness and recall, especially for underrepresented lesion types. Third, I observed that lightweight CNNs work surprisingly well in federated settings. The compact CNN performed effectively without requiring large resource intensive models, which is great for low resource edge services. Lastly, FedOPT turned out to be better suited for real world heterogeneity. Its adaptive nature led to more stable convergence and slightly higher accuracy than FedAVG, making it ideal for non IIT medical data scenarios. Limitation and challenges. So, one major challenge was client drift over rounds. Even with upsampling, variation in local updates caused some mild drift in client models, which highlighted the need for adaptive strategies like FedOPT. Another issue involved edge cases in upsampling. In hospitals with very few examples of rare lesion types, the repeated upsampling of those few images led to overfitting risks. Also, this was a simulated study with only 5 clients. Real world federated deployments at scale, like 50 or 100 clients, may behave differently, both in terms of convergence and stability. And finally, privacy wasn't addressed in this study. Although federated learning inherently avoids sharing raw data, I didn't implement differential privacy or secure aggregation, which would be critical in a real healthcare setting. So, while the results are promising, these limitations open avenues for future work. Finally, let me walk you through the future directions for this project. First, I plan to integrate differential privacy and secure aggregation techniques like DPSGD and secure multi party computation. This will help ensure patient level data confidentiality during training, which is essential for complying with strict healthcare regulations like HIPAA and GDPR. Privacy wasn't implemented in this version of the study, so that's a key area for improvement. Second, I want to move beyond simulated clients and test this pipeline in real hospital environments. That means handling real world challenges like network latency, client dropout, and noisy data. And third, I see a great potential in integrating AI agents for workflow automation. For example, LLM powered agents could help explain periodic predictions to clinicians, auto tune hyperparameters per client, or re-trigger training when concept drift is detected. I plan to use frameworks like LangChain and CrewAI to build those modular and intelligent agents that can assist across the ML lifecycle in a federated setup. So, yeah, that's it. Thank you.
Great. Thank you, Priyanka. I think very interesting master project. I have a couple of questions, and if some of you in the audience have questions, feel free to ask them. We keep an eye on social media to see if there are some questions. So my first question, maybe I missed it when you were starting your presentation. The model you use, is it a pre-trained model or are you training from scratch?
From scratch.
From scratch, okay. And did you consider using other models, or basically did you analyze different type of model architectures, or maybe early in your project you found one that worked well and you continue?
No, so this was actually a very basic demo project. I wanted to just see that how CNN works with federated learning. So this is my first FL project.
Okay.
So I was just trying to see how it works, and I did not use any LLM models or anything. This is or pre-trained models. This is like from the scratch.
Okay. Yeah, that's fine. I think typically a simpler solution is the right thing to do
Yeah,
right at the
in
beginning.
healthcare, I think it is better to use simpler models. If it is like very heavy, then it's difficult.
Mhm. Okay, fair point. My next question is, so I saw you have 5 clients, which I think is okay. I think it's common to have maybe a federation of 5 hospitals. It's not so common to have a federation of 10,000 hospitals, even though that kind of number of clients is something you might encounter in cross-device FL. My
Mm.
question is, you have 5 hospitals, but why did you also decide to go for 5 rounds only? Maybe in your experiments you saw that turning for longer was not beneficial, or you started to see some overfitting. Can you comment on why 5 rounds?
I think the number of classes were almost similar to the number five,
Okay.
and that was one of the reasons. But yeah, I thought that I don't know, like I just wanted to start with lower number, and because that itself initially when I was doing the fedavg, that itself was like when I was trying to do the upsampling in that, it started to overfit. So at that time I did not know how to prevent it. So later on I got to know that okay, there is another option for it, fed opt also. So when I implemented that, it improved a lot. So yeah, I did not actually consider improving or increasing the number of clients.
Okay, no worries. I think it could be interesting to see how the system behaves when you make it a bit more challenging. So, um,
And
yes.
also with the yesterday, I think your 1.20 version was launched, I guess. And yesterday itself, I did this project. I mean, the second one, the Fed OPT one. So
Oh,
it actually reduced the training time significantly. So earlier it was taking more than an hour, and this time it only took hardly like like almost 19 minutes.
oh, so the OPT experiment, you just did it with the latest version of Flower?
Yeah,
Okay,
yes.
amazing. That's great feedback to see that actually the features are working. We knew they were working, but it's great to. I think you're the first person that I hear experts on saying that it worked very well. So thanks for sharing
Yeah.
that. So I have my final question because we are running a bit over time. So you
Mhm.
presented some very interesting points as future work. Are you planning
Mhm.
to work on them maybe as a
Yes.
PhD, or are you starting your research career? Do you have some things you want to share about this, or which of these points you want to tackle first because you had a long list?
I want to like merge 2 points. First is that the I want to include some AI thing into this. So my model till now is doesn't have anything related to AI, but like AI agents or something. Later on, I also and yes, the privacy related things like differential privacy. So those things I want to implement.
Okay. And final question, because I think we have a question on X, uh,
Mhm.
or somebody told me that we have one. Can
Okay.
you show the slide very briefly of what the model architecture you implemented?
Mm, yeah, this is the one. Sorry, I'm not sharing screen, I guess.
No, you're not showing. I think yes. I remember it was a small CNN.
Model architecture, you mean this one or the
No,
CNN structure?
yes, the CNN structure. Yeah.
Okay. So this is like a very generic. So this is not
Yeah.
exactly what I am doing, but
Yeah.
this is a generic thing. So this is the actual thing which is
Okay.
present in my.
Okay. So Makes sense. Like 3 convolutional layers with max pooling in between, and then 2
Yeah.
federated layers. Okay, makes sense.
Yeah.
Okay, yeah. Thank you very much. I think I think it's super interesting master thesis work. So I encourage you to keep working on federated learning. I think it's a super interesting research area.
Thank you.
Thank you very much.
Yeah.